Okay, we want to talk about acid-base reactions. And salt hydrolysis. There are four types of acid-base reactions. Strong acid plus strong base HCl and AOH as an example. Weak acid plus strong base acetic acid and sodium hydroxide. Then you have a strong base plus strong acid plus weak base. And HCl and NH4OH. And then we have weak acid plus weak base. HOAC and ammonium hydroxide, like this. In each case, when you titrate an acid into a base or base into an acid, we generate a titration curve that has an equivalence point at the neutralization of the acid or base and base. So for an example, if we have a base into acid, you'll have a titration curve that will start at a low pH and concentration of base and generate a titration curve that has this trend. And this point at the inflection, in the middle of the inflection, is called the equivalence point. Well, for a strong acid, strong base titration, equivalence point is pH of 7 always. For a weak acid, strong base, the pH is always above 7. For a strong acid, weak base, the pH at the equivalence point is less than 7. And for weak acid, weak base, pH is proportional to the K value. Stronger, larger K value dominates the equivalence point. What we need to do now is take each one and show how that how the equivalence point is affected by changing the type of acid-base reactions. We'll start out with a strong acid plus strong base. Reaction. For example, if we have an HCl plus an NaOH reaction, we find it produces the salt NaCl plus H2O. Now, we'll call this reaction 1. Reaction 2 will be the ionization of the salt. If you recall, salts are the same thing as ionic compounds, and this will ionize into the cation sodium and the anion chloride. Then you have reactions that are tested as reacting with water, 3 and 4. So we take each ion and we react it theoretically with water, and I'll write it in this format. This is the plus part and this is the negative part of water, of course, and then we'll test chloride reacting with water in the same context and see what the outcome is theoretically. So sodium being positively charged would theoretically bond with hydroxide, and we'd have sodium hydroxide. And chloride would bond with the hydroxide, and we theoretically have HCl plus an excess of hydroxide ion, or an excess of hydronium ion. Well, the question is, will these reactions occur? And what you should look at is what is theoretically produced. If it is a strong electrolyte, in this case strong base and strong acid, the reaction will not occur. So you will not have these occurring, and you would list no reaction. So what is the pH dependent on in a strong acid, strong base titration? The pH at equivalence point depends only on the autoionization of water. That is, H2O plus H2O goes to an equilibrium, H3O by proton transfer and an hydroxide. And of course this is simplified into H2O going to H plus plus OH minus. Well, at equilibrium, we ignore the water, we find the concentration of the hydronium ions 10 to the minus 7 molar, and the concentration of hydroxides 10 to the minus 7 molar at 25 degrees Celsius. And with this, we can calculate the pH now to equal minus log of the hydronium ion concentration, which is equal to a minus log of 10 to the minus 7, which of course is minus 7, and gives you a pH of 7. For any strong acid, strong base titration, you will have an equivalence point at pH equals 7. For a weak acid, plus strong base titration, we use acetic acid in reaction 1, that'd be HOAC plus sodium hydroxide going to sodium chloride plus sodium acetate. Sodium acetate plus water. Then we take the salt, the sodium acetate, ionize it, Na plus OAC minus, and then 3 and 4 will be taking each ion and reacting with water, hydrolysis. So Na plus HOH will go to sodium hydroxide and in excess of hydrogen. And then the acetate ion will react with water to produce the acetic acid plus an excess of hydroxide. Well, reaction 3 will not occur because theoretically we're producing a strong electrolyte in sodium hydroxide. But in reaction 4, since we're producing a weak electrolyte, acetic acid, yes, this reaction will occur. So the analysis is based upon the concentration of salt that it delivers a negative ion at the equivalence point. So let's assume the salt concentration is 0.10 molar. And the analysis, we ignore the, let's do this, Ci is 0.10 molar. In the analysis, we ignore the water, OH. We ignore the water and calculate what the acetic acid and hydroxide concentrations are, and then when we get the hydroxide, we can get the pH at the equivalence point. Well, this is a conjugate base, and conjugate bases are identified in hydrolysis reactions as a Kb prime for the salt ion, in this case the acetate ion, and is the products, HOAC, and OH ion concentrations divided by the salt, which is ions, the anion. And so this is substituting the equilibrium rho, we have X squared over the 0.01 molar, and this is the Kb value. Well, Kb is calculated from a expression Ka times Kb equals Kw. And so solving this for the Kb, it'd be Kw over Ka. So that would be Kw over Ka. And that A is for the acid that's generated when the anion reacts with the water. So this is acetic acid, and Ka for acetic acid is 1.85 times 10 to the minus 5. And so we put that into here and then solve for the X. So now X is equal to the square root of 1 times 10 to the minus 14 times 0.01 divided by the Ka, 1.85 times 10 to the minus 5, and all that would be in moles per liter. And so this will, of course, be the hydroxide ion concentration, and that will be give us 7.35 times 10 to the minus 6 molar in the hydroxide ion concentration. So now, I'll move this up, got that down. So now we take the POH being minus log of the hydroxide concentration minus log of 7.35 times 10 to the minus 6, and that's 5.13. And remembering pH plus POH equals 14, we can calculate the pH now. 14 minus POH, which is 14 minus 5.13, and it's 8.87, which is a basic solution for a strong acid, weak acid, strong base titration. doing the same thing for a strong acid plus weak base, we can determine the pH at the equivalence point. If we take, say, HCl and weak base NH4OH, which will give you an ammonium chloride plus water. And so that'll be reaction 1. Reaction 2 would be ionization of the salt. Goes to NH4 plus Cl minus. Now, testing each of the ions from the salt, I'll start with chloride plus HOH. We find it forms hydrochloric acid and the hydroxide ion. Well, since this is a strong electrolyte, no reaction. But the ammonium ion will form a weak electrolyte when reacted with water. And this will set up an equilibrium between NH4OH and excess hydronium ions, like that. So if we assume a 0.10 molar salt that comes out of the acid-base reaction, we're looking for X, and X being the hydronium ion will lead us to the pH. Now, since this is a cation in this reaction, we're talking a Ka value or a Ka prime value for the NH4 ammonium ion, and that will be calculated from the Ka times Kb, which would be Kw over Kb of the ammonium hydroxide. Well, the Kb of ammonium hydroxide, well, I'll put it up here somewhere, is 1.85 times 10 to the minus 5. And that will, of course, go down to the Kb value in this expression. And then you have products over reactants from the reaction of the hydrolysis of the cation with water. Yes. So now we have putting X and X, and then the 0.1 in the salt position, 10 to the minus 14, and the Kb, excuse me, of the ammonium hydroxide. We have 1 times 10 to the minus 14 over 1.85 times 10 to the minus 5 is equal to X squared over 0.10. And again, solving for X, which is the hydronium ion excess, a little better, is equal to 10 to the minus 14 times 10 to the minus 1 divided by 1.85 times 10 to the minus 5. And take the square root of that, and the hydronium ion concentration is 7.35 times 10 to the minus 6 molar. And so we take that and calculate the pH at the equivalence point, minus log of 7.35 times 10 to the minus 6. and that gives us a 5.13 pH at equivalence point for the weak base, strong acid titration. Well, next time we will get into common ion effect, buffers, and acid-base titration calculations in the next class.